So when we replace the natural log sequence with its power series, we can essentially do all of the algebraic manipulation based off of that, instead of having to compute derivatives. In many ways, the derivatives are for natural log are already encoded and embedded into the Taylor series. And so if we were to write this out, well, what's the Taylor series? It is x minus x squared over 2 plus x cubed over 4, or 3, minus x to the 4th over 4, and it's going to keep going. And since we're only subtracting off an x and dividing by an x squared, the algebraic manipulations are fairly easy. So the x is going to cancel this first term here. So we'll have minus x squared over 2 plus x cubed over 3 minus x to the 4 over 4. And then I got to divide each of those by x squared. And what are we left with? So by dividing out that x squared term, sort of gives me a constant term left in the sequence. And what happens when I plug in 0 for the rest of the x's? We just get negative 1/2. So nothing too tricky there. I mean, we've seen all these kind of algebraic manipulations. It's just incorporating the fact that we're also wanting to compute a limit now and evaluate a function essentially after we've made those manipulations. So other questions. What have you guys been doing for review? Did you guys work through the practice midterms? Or any of
Yeah,
the
I went through the practice
multiples?
midterm.
Yeah. Any questions on those guys? Things you found difficult, things you want to go over?
I think I actually do have a question. I just need to open up my notebook here.
Yeah.
Yeah, I was wondering if we could go over number 4 on the spring 2018 exam you emailed out.
Yeah. Let's see. Spring 2018, number 4. Okay, so this is like a vector field slope thing.
Yeah.
Let's see. So below is a slope field with slopes labeled. Use Euler's method in a step size of h equals 1 to obtain an approximation to y of 2 for the initial value problem. So we're starting at minus 4 equals 4. Sketch a piecewise linear approximation and fill in the relevant information on the table. So if you look at the graph, so we're also, not only are we given the points, so our standard xy coordinates with the x and y coordinates listed on the outside, but these values inside are the slope. So what we want to do, so at step 0, we're starting at minus 4, 4, and negative 3. On the quiz, I think most people were pretty good at this. So you kind of just have to remember the algorithm for Euler's method. And the one on the exam, it could be something similar to this, where we're just asking you to list out like a sequence of points that would come up with an approximation. So our step 0, we're at minus 4, 4, so they start up here. Then we have a slope of minus 3. Luckily here, we are using, so use Euler's method with a step size of h equals 1. It's going to be similar to how it is on the exam. H equals 1 is a nice step size just to keep the numbers simple so we don't have any sort of long decimals like we kind of saw on the quiz problem. So because the step sign is 1, we can essentially fill in the steps for x. So it's going to go from minus 4 to minus 3. To minus 2. Let me try to fill all those in. Minus 1. Zero. 1. And 2. So not too bad. Now for the y's, how do we find the y? What we want to do is take this previous y and then add on the slope, which is our y prime, times the step size. So luckily, because the step size is 1, all we have to do to find the next y value is essentially add on the slope at that point. So if I add on negative 3 plus 4, we will get negative 1. And that's essentially here at this point. So if you look at the point negative 4, 4, the slope they give us there is negative 3. And so what we want to do is go over 1s because my x step size is 1 and then down 3. And that's my next point. Now we have a new slope and they give it to us. The slope is negative 2. If in this case, so they give us the slopes on the graph, and so right here we can actually just fill in our next y prime at this point, negative 3, 1, is negative 2. The other thing you might have to do is if they actually give us the differential equation, I might have to solve this. So I can take these 2 points, I can take my x and my y value, plug them into the differential equation, and then figure out what y prime should be at that point. So you might have to do that work on your own. Here, luckily, the slopes are given to us. And so now, since our slope changes to a negative 2, at this point, we want to go over 1 and down 2. So our next point is here. So we'll be at negative 2. And then, of course, I subtract. I take 1 minus 2. And then we'll be down here. Do we have a negative 1? Sorry, so that should have been a, whoops. This should have been a positive 1. Why did it erase both of those? I don't know. So we had negative 3 here. And then we had positive 1 there. And then when I go down to, here we'll be at negative 1. And so we find this next point, negative 2, negative 1. And then what's my slope here again? So we kind of just repeat that process. My slope is negative 1. So we fill in our slope. And then now to fill in the next point, I know the x value is going to be here at negative 1. The y value, I need to go change by my slope. So we're going over 1, down 1. So my next point would be there. And we fill everything in. So points is -1, -2. The slope there is 0. And then so if the slope is 0, you essentially just want to draw a straight line to the right. So my next point is going to be 0, and we'll still be at -2. And we see what's happening to the slope. Slope is there as 1. And so you can just, I mean, so drawing it, you guys won't have to draw it on the midterm. But your piecewise would look something like that. Do you guys want to see the rest, or is that enough of an explanation? So the next one, it looks like the slope is 1, so you're going to go over 1, up 1. Slope is 2, so you're going to go over 1 and up 2. Slope is 3 here, so you would go over 1 and up 3. And those is how you would find the piecewise lines, and then you just fill in your points as you find them.
I have a question on the same exam for 3 III.
Three. Circle the correct answer. Find the sum of each of the series. III. So we have n times 1/3 to the n minus 1. So with any of these evaluate, if you're given a Taylor series, you kind of have to reverse engineer it. You either need to use a formula for our geometric series, which is essentially the Taylor series for our function 1 over 1 minus x, or look at a different Taylor series, for any of the functions that we know. And so the key thing is kind of almost reverse matching. You want to look at the Taylor series, look at what's given, and try to think, well, which is it closest to? And so in this one, since we have a fraction raised to the n minus 1, so it's shifted, it looks a lot like a geometric series. And if you pull up your sheet, let's see, so I don't have it listed on the exam, we will give you essentially what they give you on WebAssign. Let me pull it up real quick. As well as the natural log Taylor series. You want to match it. Let's see if I could find the little here. So let's take a look at the power series real quick. So you'll be given this guy. And you want to find the one that it looks closest to. So one of the problems is, well, we have something to the n. It's shifted, so shifts in n and n minus 1 shouldn't be too much different. Those are really close. It's not a 2n or a 2n plus 1, so it's probably not going to be sine or cosine. We can rule those two out. Not going to be tangent either. That's another 2n. Binomial, this one you guys don't know. And then I guess the other one not listed is the natural log. So the ones you want to think about are either e to the x, the geometric series, or natural log of 1 plus x. So which one is it closest to? And how do we recognize that? Well, this one's alternating. That's another thing that's hard to get if it's not already built into the sequence. So what we want to think of is I've got to use one of these guys and do some manipulations to get to this. If this guy isn't alternating and I start with an alternating, it's going to be hard to kind of get rid of that alternating. So we want to get rid of that guy. Just like how we got rid of the sines and cosines. Sines and cosines in the arctan had a 2n in there. And so if I start with something like that, I'm not going to be able to manipulate it to get not a 2n there. It's a little difficult. So we've got these two, and you kind of just have to pick one and think, well, which one should it be? The next thing you want to think about is, well, this one has an n factorial in the denominator. And if I were to try to manipulate this guy to get to here, I would somehow have to get rid of an n factorial. And hopefully through the process of sort of this chunk of the semester working on Taylor series, you kind of understand, well, I'm not going to be able to take derivatives or integrals of this guy, especially because derivatives and integrals of e to the x give me the exact same thing. And I will get the exact same power series. So getting rid of that n factorial is going to be hard. And so your thought process should ultimately lead, okay, maybe this guy's the easiest one to match it with, to start with. So let's try to start with that. So we want to start with 1 over 1 minus x, and that's going to be just the sum of x to the n. And what do we need to do? Well, I need an n minus 1, and I need an n minus 1 in the exponent, and I need an n out front. The 1/3 to the n, any of these constants, you can think of just evaluating x there. Right? If I had a 1/3 in for x, that's essentially what it is. We want to do the algebraic manipulations first and differential manipulations before then evaluating it. So what do I need to get an n down out front? We take a derivative. And then my series looks like this. And that looks really close. What is the starting value? So even if I started at n equals 0, it would just kill the first term because it would be 0 times something. So we can actually shift this, as we've seen with a lot of derivatives. Anytime we take a derivative, the series naturally shifts up by one index of its starting value. And so since I took a derivative on this side, we take a derivative on the left. So we get 1 over 1 minus x squared. And so, of course, that was just, 1 minus x to the negative 1. So we'll have negative 1, 1 minus x to the minus 2, and then times that extra negative cancels out that negative for that derivative. So I know these two functions are equal. And now, since I have the right power series, we just want to evaluate at 1/3. So we'll get 1 over 1 minus 1/3 is the sum of the series we were given. And this guy we can just compute. So that's going to be 1 over 2/3 squared, which is 3/2 squared, or 9/4.
It's nice to learn that trick.
Yeah. Other questions?
There's one in the chat.
Can we go over error estimates for Taylor series and Taylor's inequality? Yeah, let's see if we can find a question. Let's see, were there any on the... Let's see, there's number 5 here, which is a little difficult. Did anyone find one of these or encounter one of these guys on any of the other practice midterms? Otherwise, we can take a look at number 5 here. So let's take a look at this guy, number 5 on that same midterm. We've got f of x is equal to 1 plus x to the 1/3. So it first has you compute the first 3 derivatives. And then, so we're going to go through a bunch of different steps. We're going to use this to approximate cube root of 2. And then we are going to find an error bound in the last part there. So in general, if we wanted to come up with an error bound, so we would want to come up with a Taylor polynomial for this guy. And in general, you want to come up with a derivative, a formula for the n plus first derivative. So we often just start by taking derivatives. So we will have 1/3, 1 plus x. When I subtract 1, we will get negative 2/3. My second derivative is going to be minus 2/3 times 1/3. 1 plus x to the minus 5/3. And third derivative is minus 5/3 times 2/3 times 1/3. Sorry, negative 2/3 there. Then we have 1 plus x to the minus 8/3. So for this problem, this is all they ask us to do. Let's go through this problem first, and then maybe we can talk about what might happen if I wanted to compute n number of terms, or if it might say like how many terms should I compute to be within a certain margin of error. So our degree T2 polynomial centered at x equals 0, we want to evaluate these guys. So if we want to evaluate, so our goal is to approximate cube root of 2. Which corresponds to plugging in 1 for x. So my x value equals 1. We're going to expand the Taylor series at 0, which means I got to evaluate all of those guys at 0. And this means that the interval we care about is between those two guys, so 0 to 1. So what we have to do with these Taylor polynomial approximations, when we want to use the error bound estimates, we need to, in general, we usually come up with an arbitrary formula for the nth derivative. If I'm only given a fixed number of derivatives and want to know, say, how close I am based off of those number of derivatives, then all we have to do is give a maximum for that one extra derivative. So if you look at the problem in part 3, we're only finding T2, a second-degree Taylor polynomial. So what did we have to do? We took the third derivative. And so this is our one more derivative than the degree of the polynomial. And so we want to bound our third derivative on that specific interval. And so third derivative, it's going to be negative. And actually, sorry, so we want to bound the absolute value of that, I should say. So the negative actually isn't going to matter, but let's write out the function just to simplify a little bit. It's going to be 5 times 2 times 1 over 3 cubed times 1 plus x to the negative 8/3, which is negative. I'm going to keep writing the constants as separated out. Sorry, when we take an absolute value, the negative will go away. And so what's going on with this function? If we want to find a bound for a function on an interval, things you want to consider is it increasing or decreasing? And are there any critical points? So just like we did in Calc 1, if I want to find the maximum value of a function on a specific closed interval, then, well, you would have to take another derivative, find critical points to see if there's any local max or min, and then check the endpoints. That is a lot of extra work. So we are kind of relying on you guys being, pretty decent Calc 2 students at this point to start recognizing some of these functions and, well, what's going to happen with them. So what is 1 plus x? It's a negative exponent. Negative 8/3, it's almost like to the negative 3, but not quite, right? 8/3 is close to 9/3. Since it's a negative exponent, if I have a 0 here, we'll get an asymptote. So when x is negative 1, we have an asymptote. When x is 0, we can plug in that value. That's pretty easy. It's just 1 to some power is 1, and then it's just this constant. So 5 times 2 times 1, what is that? So that's 10/3. It's about 3. So I know there's going to be an asymptote. It's going to go through that point. And then what's going to happen? Well, hopefully you guys are, we know how to graph 1 over x, which means you should know how to graph 1 over x plus 1, right? That just shifts everything to the left. And then if I raise that to successive powers, what's that going to do? Well, it's just going to make it still decrease. Hopefully you guys recognize at this point that these types of curves aren't going to have any critical points, that it is just going to be a decreasing function. And the interval we care about is from 0 to 1. And so because this is a decreasing function with no critical points, then the maximum of the third derivative is going to be on the left side of the interval. So we can take m to be the value of the function at that point. So that is our m. When we want to find our degree 2 polynomial, let's reevaluate these guys. So our f of 0 is 1. F prime of 0 is a third. F double prime of 0 is negative 2 over 3 squared. And then F triple prime, we don't actually need. So of course, this part was, we just want to find T2, our second degree Taylor approximation. So we need our second derivative. We are evaluating at a equals 0. And then, so what are my constants? My C0 is just 1. C1 is just 1/3. And C2, always be careful. The first two are misleading because the first two constants are always going to be the value of the derivatives, and the value of the function and the value of the first derivative. The second constant, you take this guy and then times 1 over 2 factorial, which is just 2. So our T2 of x is 1 plus 1/3 x minus 1/3 x squared. So the last two parts, if we wanted to approximate cube root of 2, again, cube root of 2, it was just f of 1, which we are now approximating by our Taylor polynomial evaluated at 1, which is 1 plus 1/3 minus 1/3. And so we just get 1 as an approximation for that. Probably not the best approximation. But then part 5, we actually want to know how far off is this approximation. So how far off can it be? Our error in the degree 2 polynomial, I know, is always less than m over n plus 1 times, actually here, so let's write out the formula.
As far as your m, isn't it supposed to be 10 over 27? I was just calculating it.
Did I miss a factor of 3?
I think you're supposed to.
Oh, yeah,
it's 3
I wasn't
cubed.
copying those. 3 cubed, yep. Yeah, so 10 over 27. Thank you for that.
Yeah, no problem.
So we want to fill in all the values there. So our m was 10 over 27. And then our n was 2. So 2 plus 1 gives me 3 factorial. X minus a, nicely enough, is just going to be 1 minus 0. And so that'll just give me a 1 cubed. So what is our error? We will have 10 over 27 times 1 over 3 factorial, which is 1/6. And so what do we get? Something like, so that 2 will cancel with that guy. And then so we get 5 over 81. Is our margin of error. Other things we can ask. We can say things like, what is the range or what is the maximum margin of error on a certain range? So we found this degree 2 Taylor polynomial, and let's say I change the question to like, what is sort of the maximum error on, say, minus 1/2 to 1/2? For this approximating polynomial. So we've got to use different numbers now, because now I've changed my interval. Since beforehand my interval, I was given a specified x value, I wanted the error based off of that interval. Now we've changed the interval, so we got to find a new m. The same analysis applies, though, at least in terms of the function. So our third derivative looked like this, where it crossed here at 10 over 3 cubed. Or 10 over, yeah, we'll just write it as 10 over 27. The problem is now I changed the interval to minus 1/2, 1/2. And so where's the maximum value going to be? Still on the left. We just need to figure out that value. And so we use our third derivative, our x triple prime of negative 1/2. And what do we get? So we had 10 over 27 times, now 1 minus 1/2 to the minus 8/3. And this is where it gets a little tricky numerically. So this is 1 minus 1/2 gives me 1/2 to the minus 8/3, which gives me 2 to the 8/3. And of course, we can't compute cube root of 2. We want to pick a nice number for this. But as I said, pick something slightly bigger than that. We want to pick the smallest integer, essentially, that I can maybe approximate this guy. If 8 was a 9, it would just be 2 cubed. And that we can compute. So a good m for that would be 10 times 8 over 27. Or 80 over 27. We would then use that, plug it in the error formula with the same numbers essentially for n, and then that would give us our maximum error on this new interval. Other questions?
Sorry, so m is the maximum value of the n+1 derivative, correct?
Exactly. Yep.
Okay. And so that's how you're getting that 18 over 27 is it's just the next derivative in the maximum value of it.
Yeah, exactly right. We took a degree 2 polynomial, so our next derivative is the third derivative, which was this guy.
Cool.
Yeah, and then we want to find the maximum value of the third derivative. the absolute
Cool.
value of the third on whatever specified interval we're working with.
Awesome. Yeah, that makes a lot more sense.
I guess the only other thing that we ask commonly on this is something like, well, now let's say I want to actually solve for the number of terms. Let's say I don't like this margin of error, or whatever margin of error this would give me, which we can fill in. So on the interval 1/2 to 1/2, we have our margin of error was what, 80 over 27, and then that divided by 3 factorial. Which is now 40 over 81. So if we don't like that and we want to meet a quota, we want to be within a specific margin of error, those ones can get a little tricky. For, let's say, Rn to be less than or equal to, I think the one on the exam is something like 1 over 20, 2000. This is like 2 decimal places. And we want to specify an interval. Let's pick a nicer interval. Let's go back to the interval of 0 to 1. When we don't know n, we have to find our formula for the general derivatives. So we had f of x is 1 plus x to the 1/3, f prime of x 1/3, 1 plus x minus 2/3, and then we keep going. And if you keep taking derivatives, what you want to look for is a pattern. So for example, if I take one more derivative, we can see what's happening in the denominator of the constants. One derivative, I have 1/3. 2 derivatives, I have 3 squared. 3 derivatives, I have 3 cubed. So that one's not too bad. My 4th derivative, I should have 3 to the 4th. The numerator is going to be hard because we haven't done a whole lot of examples of advanced sequencing. You guys had a WebAssign problem with similar to this, where there was a product, a successive product, but it's not a factorial, right? It's not 5 times 4 times 3 times 2 times 1. It's 5 times 2. And what's the next one going to be? It's going to be 8 times 5 times 2. I'm going to leave off the times 1 for now, so maybe we can kind of see a pattern. What are we multiplying? We're multiplying successive. Each of these has a distance of 3 apart. And we've seen linear sequences where I just add 3 every time. But instead of like adding the numbers together, we're actually multiplying then those numbers together. So this example isn't perhaps not the best, because we do want you to come up with an arbitrary formula for the n plus first derivative. So let's practice at least picking out the parts we know. So when you do that, you're really picking out, well, what's going on with these constants? I have a constant exponent, and then I have these constants multiplied out front. And the denominator, we at least saw that every time I take a derivative, that I'm going to get this extra power of 3 from the constants in the exponent. So my denominator is just going to be 3 to the n plus 1. The exponent on this polynomial term, a little trickier. Okay, so 1 derivative, I'm at -2. 2 derivatives, I'm at -5. 3 derivatives, I'm at -8. Of course, the denominator is always 3. What's happening to the numerator? I am subtracting 3 every single time. So it's going to be a minus 3n, but then I need plus or minus something. And so let's take a look. So one derivative, I'm at -2. So if I plug in 1 for n, I have -3. How do I get to that -2? We need to add 1. And let's check that. So 2 derivatives, when n is 2, I will have -6 plus 1 gives me -5. 3 derivatives, I'll have -9 plus 1 gives me that -8. So that's the numerator of the exponent. And of course, the denominator is always a 3. So those parts you guys should be able to figure out, right? This was just a linear sequence of the numerators, constant third in the denominator. And of course, they're going to affect this. This numerator is a little more complicated. Notice that the second derivative, it starts essentially 1 behind this. So if this is -3n plus 1, it'll be -3n minus 2. Or should I have plus? Might need a +4 there. Hang on. So what happens when n is equal to 2? We will have -2, or excuse me, -6 minus 2, and that does not give me that 2. So we actually need a, sorry, we need a +4. We need to go in the opposite direction, but that was a -3n. So that's where that plus comes for, is the first number. But then you're just multiplying by a successive number of terms, which you won't have to find a sequence for something like that. But then what would our process be? So let's at least go through that. We would want to find m. And again, this is just finding a maximum for a function. Now, except of course the n's are arbitrary. The same analysis would apply though. What's often, especially with a negative exponent here, it's going to be a decreasing function. The only thing that's going to change is the constant multiple out front. It's going to be in terms of n, so that'll change. So it will still be on the left end here. So we would find that value. We're taking absolute values, so there is one thing I guess I did forget here, is what's happening to our derivatives. It should be alternating. So we would also have a -1 to the n. And looks like it's going to be n plus 1. So that way when I take 1 derivative, it'll be positive. 2 derivatives, it'll be negative. And then alternate. And so when I plug in 0 here, what are we going to get? We'll get this constant out front. Actually, that negative shouldn't be there because I encoded that there. Actually, man, I'm messing on this numerator up. Ignore the numerator. So whatever that constant is in the numerator, let's just call it whatever the numerator constant is as c. Sorry, I don't want to waste too much more time on this, and that's going to be something way beyond what you're ever going to be tested on. And of course, since I add in, or I plug in x equals 0, we would just get whatever that numerator constant is over 3n plus 1. And our last step would then be to solve the error equation with whatever margin of error we get. This one can be a little tricky, primarily because of that factorial. X minus a was just 1 minus 0, so it'll just give us a 1. And what do we have? We'll have an equation that looks like this. So unfortunately, because this problem wasn't originally written to ask this type of question, the numbers aren't too nice. I will say there is a problem like this on the midterm though, and you do want to show all your work. It's going to be one of the written problems. So if you get to something like this, one big warning I want all you guys to do: don't use calculators. Please, 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 please don't use calculators. Because if there's evidence of you using calculators, that is cheating. And I will have to give you a 0 for the entire midterm. So don't use calculators. Don't come up with crazy decimal answers. In a case like this, we would have to solve for n. And even if it's factorials, I know sometimes those are a little tricky. Usually you can manipulate it in such a way so where it'll look something like, 20,000 or 2,000 is less than or equal to 3 to the n plus 1 factorial, and then whatever that constant was in the numerator on the problem given on the exam, it's going to look, a lot easier to find the formula for that. And if you have to guess and check with something like this, you might have to just do a few calculations. Your n shouldn't be very big, right? I shouldn't find n equals 5, because if n was 5, you'd have to compute 5 factorial or 6 factorial. 5 plus 1 is 3 to the 6th. It shouldn't be that complicated. It should be within like n is like 1, 2, or 3 maybe. And there might be maybe one multiplication you have to just kind of crank out by hand. And all we need is to find the smallest n where that's bigger than 20,000. So let's check. Let's just say C was 1, and how you might do a computation like that. Well, we can check something like n is equal to, let's say, 3. And then so we'll have 3 to the 4th times 4 factorial. That's going to be 81 times 4 factorial is 4 times 3 times 2, so 24. And now it's where it's like annoying. You got to multiply 81 times 24. It's kind of just time consuming. But really, we just want to see if it's bigger than 20,000. So what do we get? 81 times 20 is 162. Plus 4 times 81 should give me 324. So that's going to be what? 1944. So not big enough, but really close. So what's our n going to be in this case? One more. And I don't want to even compute that, but we should be able to recognize that if I have n equals 3, this is how big as the number is. If I plug in n equals 4, by the rate of growth of those functions, it's going to easily jump over that margin. And so n equals 4 will be our answer. Conversely, the other types of questions we've seen with this is to find the interval. And again, this might be something we ask on the exam. Let's go back. So let's find our here. So let's say we still are working with T2 of x, and we ask a question of how big can x be? So now we don't know the interval. I know it's centered at 0, but I want to know how big of an interval around 0. Let's see, how big of x if on the interval. the margin of error is less than a certain number. Let's pick another number. Let's say, 10,000 or something. Or even, let's just pick the same number. Let's say less than 2,000. So what's the information we're given? We're given n. We're given our error. The thing we don't know is our x. Right? So our equation is always thus. X minus a. A we're almost always given because we know where we're expanding the Taylor series. And a better way to kind of write this is perhaps this. Because anytime I'm given an error, I want to take this formula and set it less than that. So we're given this side, we're given m, or we can find m at least. We're given n, we just got to solve for x. So since our n was 2, sorry, I messed that up. We don't know x. We get an x minus our a was 0. And what was our m? So since n equals 2, we found the m by taking a third derivative, and then we want to bound it by our x. Unfortunately, we've got to change it because now we're on an interval from minus x to x. Where is the maximum going to be at? What did we have? We had 10 over 27. 1 plus x over negative 8/3. So the maximum is just going to be at the left end. And even if, I don't know if it's confusing to pick, I'm kind of overusing the variable x. We could change the x's to like a c to just know how big of an interval from minus c to c. And it's going to be at the left end again. 1 minus c. And so that's going to be the maximum. We run into a problem or some difficulty here because we've got our m is based on how big x is. And then, so I changed my x's to c's based off of that. So that'll be a c cubed. And now I have to solve this equation. Is all that making sense, at least in the process? So it's all the same equation. You just have to remember what you're solving for. And in this case, we are solving for our x value, how big the x's can be, or I called it, instead of kind of confusing the x's with maybe a finite end of the sequence or of the interval, we can change the x's to c's. And I want to solve for this c value. Be very careful with a question like this because, again, you cannot use a calculator. So this one we're not going to be able to solve because this was a problem that wasn't written for this type of solution. But in general, if I were to solve for c, you would have an expression maybe involving things like cube roots of numbers and all that. Leave them as that. Don't type those in a calculator and write decimals, because if you do, it's clear indication of cheating. Any questions? So sorry for, not having a great example with this pulled up. There's kind of been a ton of problems written. Of course, in something like this, let's assume if we could, sometimes when the function we originally given in this case was really the problem, that when I take successive derivatives, we get more and more complicated constants, and it's kind of hard to find a specific bound. Usually the m is not going to be this complicated. So like if the m were just 1 or a hard number that we could plug in there, solving for c is pretty easy now. I just have to multiply the constants over and take a cube root, and then just keep it like that to find the range in which we would want to use this Taylor approximation for that given error bound. Other questions?
If there were a written problem about like exponential growth or something like that, do we need to like go from the very start and like prove the kind of function that you use, or can you start off with that exponential growth function and then just go from there?
What do you mean? Oh, you mean
So
like for differential equations?
yes.
Depends on how like if it's a differential equation that's like dp dt is kp, and you just go that p is equal to c e to the kt, I'm fine with that. You guys have seen this hopefully in every math class since pre-calc. Hopefully you guys have seen it, and solving this differential equation, I think everyone's fine with. Other questions? So hopefully everyone's comfortable with computing Taylor series. I think you guys are getting pretty decent at that. Finding, kind of like what we started with, either given a Taylor series and asked to evaluate it, or sometimes we're given a function and then asked to find the Taylor series. All of that kind of stuff really amounts to just knowing the Taylor series that we've worked with a lot. And again, you'll have a table with all those, but then being able to kind of pick out your starting point. So if we're asked to, find a Taylor series for a given function, you should be able to, say, well, that function is either close to an exponential or it looks a lot like a 1 over 1 minus x, and then figure out the steps to get from a known function to the function you're given, and then trace those same steps for the power series. I think most people are getting pretty decent with that. And then, of course, the opposite end, like we saw when we started with, is sometimes we're asked to evaluate a power series that may not look exactly like one of the given functions. So we kind of have to see, well, given the power series, what manipulations do I need to do on a well-known power series to get to my given power series, perform those exact same manipulations on the function, and then evaluate. those guys you're getting pretty decent with. Finding the interval of convergence. Make sure you guys review that. Just a ratio test essentially there. Careful with your algebra on intervals of convergence, though. I think that's the common mistake, especially with factorials, is either not working with the factorials correctly, or sometimes it's just easy to forget and make a brain fart and not write something down correctly. So double check your work, especially on the multiple choice. Be very, very careful on the multiple choice. Just because some of the answers might look very similar. And so you can easily just misread one of the answers and then end up clicking it, even though you meant to click a different answer. And the multiple choice ones are, I think they're like 6 or 7 points. So it really sucks to, miss a multiple choice for something as stupid as that. Differential equations, most people are fine. Separable equations, I think most people are fine with. Euler's method we went over. Actually, you guys seem pretty good with Euler's method. But again, that's kind of just an algorithm. You guys seem fine with following algorithms and evaluating functions and formulas when you need to. I would say review these error-bound type problems. So take a look at the exams and see if there's any more that you guys want to practice. I don't know if I'll have time to jump on before the exam. I can say a little later after class if you guys are interested and keep office hours for like, I don't know, an hour or so.
Yeah, that'd be nice.
Well, if you guys have questions now, let me know. Maybe let's go through and look through some of these exams that I sent out and see what we got. And I'll see if any of them might strike a bell. Interval of convergence. How do you guys feel? Do you guys want to see an example like this? Number 1.
For sure.
On the exam is just find an interval of convergence. I almost want to do another one of those estimation problems, but with an actual numbers pre-worked out instead of us trying to modify a given one, because those numbers in the last one we were doing and the function itself just wasn't something that was going to play nice with a Calc 2 level midterm. So we want to find the interval of convergence of this guy. And interval of convergence actually doesn't matter. Wherever the starting value is, doesn't really matter what's written on the sum. All that really matters is the terms themselves. And then, so some things to remember, that the center is always this guy. Most of the time it's 0, but sometimes it's not. We'll write it as a equals 5. And so the radius of convergence, I would say a good thing to review might be some of those abstract questions that we've seen, even on the last exam. No, did we see it on the last exam? I feel like we saw this somewhere, maybe on one of the quizzes or one of the web assigns or homeworks, where it kind of gives a question where abstractly we might ask, say, there's a function and it's something like bn x minus 5 to the n. And I could give you points. I could say this function converges at -2, but diverges at, I don't know, 10. So we've seen a question like this somewhere. Maybe, I think it was actually on the written homework.
There was one like this on the last exam.
On the last exam is where we saw it? Okay.
Yeah.
And then it was kind of like, well, what happens at these other points? Or what can we deduce? And we kind of gave some ways of doing that just based off of the alternating series. We kind of can estimate the rate of growth or the rate of decay of my constant sequences and then determine, well, will that be enough decay to converge at, say, what's happening at 7? What can we say? So if I were just given something like this abstractly, What's going to happen at x equals 7? Converge or diverge?
Can you move the paper down?
Oh, sorry. And actually, 7 may not be the best. What about 6? What's going on at 6?
Doesn't it start to diverge? Or wouldn't it?
So 6 is converge. Why? The other thing we can kind of estimate is that the radius of convergence. So because the center is at 5, and I know I converge at -2, I know my radius of convergence has to be at least 2. So I know that within those values, since I converge at -2, I will have to converge all here. I know I will have to converge all here. At the endpoints, though, we got to be careful, right? If the radius of convergence were only, actually, wait, that's -2. Sorry, I meant +2 for that. And then I guess that's an interval of 3, isn't it? So, right, what's the distance between 5 and 2? It's 3. So these will all converge. What's going to happen at 8? 8 is where it gets hazy. 8 we don't know. So because I know it converges at 2, it certainly converges at 5 because that's the center. I know that the radius of convergence is at least 3. So it should converge all values 3 below, all values 3 above, but the endpoints we don't know about. So it could converge here at 2, but 8 it could converge or diverge. We're not sure. At 10, I already know it diverges. So I know the interval of convergence could possibly be bigger than 2. It could be, or bigger than, the radius could be bigger than 3. But I know that the radius of convergence is 5 or less. So those are some things you can think about in terms of like what's going to happen. So if we go 5 below, what's going to happen when x is 0? Well, I know it diverges at 10. On the opposite end of that radius, if I go 5 above, I'm at 10. 5 below, I'm at 0. It could be either, could converge or diverge, because this could be the end point of the interval of convergence. One thing we do know that below 0, so if I go down to -1, we're diverging. Because that is outside the interval of convergence. I know that the radius is at most 5. And so as soon as I go further than 5 away from the center, so here I'd have to go -6 to get down to -1, we know for a fact that it will diverge. Those are some abstract things we can ask in terms of radius of convergence. If we are given the actual BNs, the actual sequence, well, then we want to compute our BN plus 1. And actually, we want to include the x's in there. Let's call it AN. So we'll have an n plus 1 over n plus 1, 3 to the n plus 1. Careful with the factorials when plugging in n plus 1s, especially if it's 2n, quantity factorial. Remember, if I plug in an n plus 1, it is 2 times n plus 1, then factorial. So we would get 2n plus 2 factorial. No factorials in this one, though, so that's our an plus 1, and then we just want to compute a ratio. So we'll take x minus 5, n plus 1 over n plus 1 to 3n plus 1. All of that divided by the original sequence. And we're also computing absolute values. So absolute values is easy enough to just make everything positive. The only time I guess we need the absolute values for the x's. But if there's an alternating sequence and there's an absolute value, you can just get rid of, you can always ignore alternating sequences in the ratio test because of the absolute values. So we simplify this, take a limit, and then set it less than 1. So what do we get? We've got x minus 5 to the n plus 1 over n plus 1, 3 to the n plus 1 times n 3 to the n over x minus 5. Need absolute values because of the x's. The 3 to the n's are going to simplify, as well as the x minus 5s. We will have an n over n plus 1, and then a 3 in the denominator as well. When we take the limit, we just get 1 over 1. So I computed the limit, I set that less than 1, multiply the 3 over, and we get an equation like this. So now we're actually told with this specific function, our radius of convergence is 3. Again, we have these x minus 5s, that's our center. And so what is the interval of convergence from that? Just add 5 to the endpoints. So we have 2 to 8. The last step with this guy would be to check the endpoints of what's going on with that specific sequence. And so what's going to happen at x equals 2? We will get 2 minus 5 gives me a negative 3, all to the n over n times 3 to the n. Be careful because this isn't always the case, but at the left endpoint here, what do we see? So that's going to give me a negative 1 to the n. Then a 3 to the n. For that numerator. So those guys cancel, and we are just left with an alternating harmonic series. And so that converges by the alternating series test. At the right endpoint, what are we going to have? We will have an 8 minus 5. So it'll give me a 3 over positive 3 to the n over n times 3 to the n. So this will diverge. So the interval is 2 to 8. So we know converge there, diverge there, and converge everywhere in between. And of course, the radius is 3 from the center. Any other questions on that? So we're out of time. If you guys got to go, feel free to go. If you want, I don't know, I can hang out for a little bit, maybe take a look at any more of these problems. Let's see what else we got. Multiple choice, find Taylor series centered at 0, matching. Those guys you should be able to do. Arctan. Arctan's one we haven't worked with a whole lot. So hopefully you're good enough at least manipulating Taylor series that if I give you the Taylor series for arctan, you can then manipulate it into finding the things you want. So key things to look out for arctan is the denominator. So if there's factorials in the denominator, like an n factorial in the series, here, let's share this. So like factorials in the denominator, those we see in exponentials, sine, and cosine. So not that guy, not that guy. The only ones that have like a linear thing in the bottom, where it's just growing like, 1 power of n, no factorials, no exponentials, just something like 2n plus 1 or even just n, it's either going to be arctan or natural log. Arctan's the one that has 2n plus 1s in the denominator. So it just grows linearly, or the n's grow linearly, constants grow linearly in the denominator. And then so you would just kind of have to figure out the numerator, plugging in an x cubed for reverse engineering that. Let's try to see, take a look. Where was that? So the arctan power series, I think it's just x to the 2n plus 1 over 2k plus 1, and then it's alternating. So you just have to get comfortable with things like so this is our arctan series. And if I want arctan of x cubed, you would just plug in x cubed there. And just be careful with this manipulation. Sometimes, it's easy to just put the 3 in the wrong position. Sometimes it's just a brain fart. But always remember, I'm taking a 3 times that whole thing. So the powers of x should be x to the 6n plus 3 over 2n plus 1. And then, of course, still the alternating. Let's see, where'd that midterm go? Find the sum of this following series. Looks like number 3, number 2, number 3 has 3 parts, 1, 2, and 3. We did part 3. Part 2, hopefully you should recognize as an exponential. Always be careful with the starting value when evaluating as well. So it should match up with the series we want to evaluate. Sometimes we leave off that first term and you have to like subtract the constant. Seen that manipulation a little bit. Geometric series, and the first one they kind of just write out an alternating geometric series. So sometimes you have to reverse engineer from, if it's just written out in an expanded form, you might have to write a series in sigma notation and then try to match that with a given function. Euler's method. Let's see, we did that one. For given a function, determining the sign of its derivatives at given points, that you guys should be able to do. Hopefully that all makes sense. In terms of like concavity, increasing, decreasing, you can at least tell the sign of the first 3 constants, the C0, C1, and C2 of a Taylor series. That was on the homework recently. Yeah, number 7 is another good abstract question that we talk about in terms of radius of convergence, similar to what we were just doing. It's got 3 parts there if you want to try those. Initial value problems, hopefully not too difficult.
Could we go over an integral problem?
Like a differential equation.
Like if we're given the integral from, I think it's, let me look. I think it's 0 to 1 of e to the x over square root of x, and we're told to find to evaluate this using a power series.
Okay, yeah. Yeah, those are actually good problems. There's one of those on the exam too. E to the x over square root of x.
Yeah, and the bounds of the integral from 0 to 1.
Yeah, so with this one on the midterm, like with those error-bound formulas, this is another one where we've seen homework problems where we want to do this and come up with an error bound. We won't throw all of that at you for these types of problems. So I think our error bound problems are just straight error bound problems like we were talking about earlier without having to do an integral involved with that. This one, I think the question might say something like, what is the evaluation or what is an expression that evaluates this? So really what we want to do is maybe come up with a correct power series for this. So really what you want to do is come up with a power series of this guy. So what we can do, I guess the proper way to do it is to use sort of the fundamental theorem of calculus and just define a function in terms of an integral. And really what we're looking for now is f of 1. And I just changed the integrand variable to a dummy variable. Shouldn't change much. But e to the t over square root of t, we want to come up with a series for, that times t to the n over n factorial. And that is t to the minus 1/2. So I'll have, t to the minus 1/2 times t to the n over n factorial. Which is just this guy. So we would just subtract off that constant 1/2 from the exponent. But now our f of x, we can write as an integral from 0 to x of that guy, our power series. And because now I wrote it as a power series, we can actually do the integral. And if we do the integral, just be careful with the constant. So I have n minus 1/2. When I integrate, I raise the power. So n minus 1/2 plus 1 gives me an n plus 1/2. I divide by that. And then that n factorial still is just hanging out. N equals 0, I guess, to infinity. That would still need to be evaluated from 0 to x. Nicely enough, now, when I plug in 0, we just get zeros everywhere. When I plug in x, we'll get x's. So we will get our power series that we care about. And now what are we looking for? Is ultimately, right, we originally started with that x value of 1. So we just want to plug in 1 there. And what do we get? Well, 1 to the n plus 1/2 divided by n plus a half, n factorial. And then 1 to the n plus a half. So because when n starts at 0, I'll have square root of 1 is 1. And then every term is going to be 1 after that. It's just going to be sum of this series.
So is that the answer?
Yeah, so that would be our answer, right? If we wanted a numerical answer, we couldn't really get it. We would have to do an error bound thing. But because we don't have there's not going to be an error bound involved in this. This was a long homework problems, and I think the quiz one, a lot of people were doing this as well. To do this properly, you need to, do this part first to get to the sequence, and then from this we would have to do some sort of error bound estimate, either using, sometimes it's nice enough where it's alternating and you can use an alternating series error bound, but then sometimes we have to do, since it's not alternating, we would have to do derivatives of that function and do another just Taylor series error bound. But we won't ask that combined with this type of question. It will be more like just find an expression for this, which would be that.
So that's the answer I got, but on where I got this from, which is, it says practice exam 2/3, that's not the answer, and I couldn't figure out why.
Were there like some extra 2's in some of the other answers?
Yeah, the answer was 2 over n factorial times 2n plus 1.
Yeah, so you just multiply that by 2 over 2.
Oh, okay, duh. I guess that makes sense.
And then distribute that 2 into that guy. Yeah. A little bit nicer way of writing it. And that does come up, right? This does come up on a multiple choice where, if that wasn't listed as the multiple choice, you got to think, well, how can I simplify this? If there's not an n, if you don't see an n plus a half, how would I simplify and kind of get rid of this half? You could multiply by 2 over 2, or you could think of, factoring out the 1/2 is another thing you could think about. And just writing, right? If you have n plus a half and you don't like that half, you could factor out the 1/2. But remember, that was in a denominator, so it would be 1/2 2n plus 1. And then I could take that divided by a half and move it up. That's where they got another way you can kind of arrive at the same constant.
What time were you thinking of having office hours, or were you able to?
So today, I don't think I'll have time to have office hours before the exam, except for now. So if you have questions now, I ask them. Happy to answer.
Number 7 on homework 11, it was x squared, the integral from 0 to 0.5 x squared e to the minus x squared.
Yeah. That one was complicated. Was the one we put on the take-home quiz.
Yes.
Yeah, not a lot of people were doing that. There's a lot to this problem. It's similar to this one we just did, except now we have an x squared and there's a 0.5 in there and a negative. So again, with the approximate it within a specific error bound, that we won't have to do for the midterm at least. But again, if we have 0 to x, let's say of t squared e to the minus t squared dt, and this is our function. then we can come up with a Taylor series for this function. And really what we want is f of 0.5. Is that on the screen? Sorry if I'm off. No. And so we want integral of 0 to x t squared. Careful with plugging in that minus t squared. Sometimes people forget the squared. Sometimes people forget the minus. But it's all to the n over n factorial. I'm not going to write in the bounds of the sum. It's always going to be 0 to infinity for e to the x. So when I distribute that, I will have a minus 1 to the n. We will have a t to the 2n, and then I have plus a 2. Since we're adding 2 more t's, or multiplying by 2 more powers of t. Now we can do the integral. And we'll get minus 1 to the n, t to the 2n plus a 3, divided by 2n plus 3, n factorial, and then evaluate that between 0 and x. And again, when we evaluate 0, it just becomes 0 everywhere. And so we just get our series.
I see where I went wrong.
Of this guy. And so what are we trying to evaluate? We now need to evaluate this series. So this would be the correct expression for the original integral. And then again, the next part is then to use an error bound to approximate this. In this case, though, this won't be asked on the midterm, because how do we approximate this with an error bound? With this guy, we would actually want to use an alternating series, because now that I have a number in there, this is just a pure series, and it's an alternating series. And alternating series error bounds are usually a little bit better. They're usually a little bit tighter. As we saw in one of the homeworks, I think using a Taylor series approximation, the correct error bound you get was like 999. And so sometimes, like, it works. The Taylor series error bound we found as 999, I think it was 4 nines, right? It will certainly be within the margin of error, but it's also overkill. It's not the tightest error bound we could find.
Where did the 2n plus 3 go?
I forgot to write it.
Okay, so it's still there.
Yep. Yeah, all the solutions for the homeworks and quizzes should be up on the Google Drive.
Could we go over one where we're given a series and then asked to find like the triple derivative at 1 or some other constant?
Like, oh, okay, yeah. Here's a good one. It's a good question. Let's say we have some function given by a power series, and let's just get some random constants in there. Let's throw in, I don't know, everything. So we have 2n minus 3, 2 to the n over, let's say, n minus 1 factorial x to the n. And n starts at 1 to infinity. Something like that. And let's say I say find. So if this is my function, I can say find the, let's say, 17th derivative at x equals 0. So one thing to note is that if I give you a question like this, the value we care about in terms of the derivative and the x value we care about is the center. All right, so this is a power series centered about a equals 0. By our formula, how did we compute the nth coefficient is the nth derivative evaluated at the center over n factorial. And so this is, you kind of just have to use this formula. So in other words, if I take my constants, multiply them by n factorial, we can recover the values of the derivatives of the function. So since I want the 17th derivative, we get that, which will be 17 factorial, which you won't have to compute. It'll be listed as 17 factorial or whatever that is. And then we need to find the 17th constant. So what is the 17th constant? Always remember that the constants match up with the powers of x. So since it's x to the n, my n is 17. So even though we're starting at 1, it just means that there's no constant term. So my n is 17, and you just plug in 17 for n. Sorry, let me try to keep both those on screen. And then this case, we can actually simplify. So we've got 17 factorial. 2 times 17 is 34 minus 3 gives me 31. And then I have a 16 factorial. And so we will get 17 times 31. And then I guess if we wanted to multiply that out, what is that? 310 plus 7 times 31, 207, 217. So what do we get? 527. If the expressions get more complicated, they'll be left with like something like this. Like if we didn't have a factorial in the denominator, that factorial wouldn't have simplified. So it might have just been written as like 17 factorial times, oh, did I miss one of the terms? I did. I forgot my 2 to the n. So we still need that 2 to the n. So C17, we had 2 times 17 minus 3 times a 2 to the 17. We also need. And 2 to the 17 we can't do. So it would just be listed there. So of course, key thing with this, guys, remember this formula. Like the abstract type of the things we can ask are like, those interval of convergence questions, which it seems like we've talked about one, and there's a couple on the practice midterms. In terms of generally understanding how do we get the constants of a Taylor series, and how might we ask questions about that formulated in these kind of ways. Let's see. Any other questions, other examples? Let me look at more on this midterm.
I have a kind of different question. I think you already went over this, but I'm struggling with finding the n plus first derivative when we're doing like the error estimates.
Mm-hmm.
Do you have any tips or tricks on that at all?
Yeah. So the key thing is, like, we have to give you a nice enough function Otherwise, it just turns into a crapshoot really fast. So you want to, usually we're finding the n plus first derivative and then finding a bound for it. So in terms of finding the bound, of course, sine and cosine, if those appear, are bounded by 1. And then the other ones, e to the x, are easy derivatives. And then the other ones that might come up are either natural log of 1 plus x or 1 over 1 plus x or 1 over 1 minus x. These ones are essentially all related, right? This one I take a derivative, I get that one. So in terms of finding a successive derivative, it's really the same for both of those two. And again, which are the same as this one as well, except that one might be alternating. So these are really the only types of functions we can ask for these types of questions. If you have to find an n plus first derivative, we won't give you any other functions other than sines, cosines, e to the x, or one of these guys. And let me check, let me think, just in case there. Yeah, I think those are the only ones that we can really give you. Otherwise, you won't be able to do it. Because if it's any more complicated than that, and even with these guys, like if it's e to the x squared, what happens when I take one derivative? Well, now all of a sudden I have an e to the x squared, but now I have a 2x. And what happens when I take a next derivative? I've got a product rule. And as soon as you start having to do product rules, every time you take another derivative, there's going to be even more product rules and just more terms, and it's just going to get messy. And so that's not something we would ask because it's a waste of time, and I don't even think the instructors ourselves would be able to find a formula for that. The reason these functions work out nicely is just because right, the derivatives, there's no chain rules involved. And if there is a chain rule, it's at most a constant. So think of like these types of functions with maybe some constants involved. So let's say I have something like we could do something like natural log of 2 plus 3x. So that's our base function. And then when we take derivatives, I get 1 over 2 plus 3x. And it might be easiest to write it as 2 plus 3x to the minus 1, minus 1, but our chain rule is going to have times a 3. I take 2 derivatives, and we get now minus 3, 2 plus 3x to the minus 2, and then I got to multiply by another factor of 3. I take 3 derivatives. All the minus 2 come down, and so we will have a minus 2 times, we'll have a 3 squared, and then, of course, from the chain rule, we'll have another power of 3 come out. And for one more derivative, I'm going to write it as, so when I pull on the minus 3, the minuses will cancel. So it'll be a 3 times a 2. Let's simplify this guy real quick. So we had a minus 2, 3 cubed, 2 plus 3x to the minus 3. I pull down that minus 3, became positive 3 times 2 times, I had 3 cubed from the chain rule of that constant. And so I will have that 3 cubed still times another chain rule, give me 3 to the 4th. And we get something like that. And so the things you kind of got to recognize are, well, what's going on with all these constants and where are they coming from when we take successive derivatives? One thing you can kind of ignore for the moment, anytime there's an alternating thing, don't let it like throw you off too much. That's kind of one of those things that for me, I think is easy enough to go back at the end and ask, am I alternating? And what should the correct index on that -1 to the n be? What's happening to these constants? So we know that every time I take a derivative, I'm going to have a constant come out from the chain rule, a constant of 3. And that's just going to increase those powers of 3. And then also every time I'm taking a derivative, at least past the first derivative, I have these numbers, these constants being multiplied out front from the negative exponent. And that's going to give me this factorial process. So we can even just do the fifth one. I know I'll have a 4 times 3 times 2 from bringing that at 4. I know that this power of 3 is going to increase from the chain rule. And of course, the exponent decreases. And then the other thing that's happening is it's alternating since we're multiplying by negative constants every single time. So it'll be negative. And so I'm kind of grouping my constants and my terms in such a way so that I can recognize the pattern. Sorry, f to the n plus 1. I know there's an alternating piece. So we'll have a -1 to the something, usually n minus 1. I know there's a factorial piece. And I know there's an exponential piece, 3 raised to something. And then we've got this 2 plus 3x piece. And now let's try to figure out, well, how do those constants match with the degree of the derivative? So the first derivative has -1 power. Second derivative, -2 power. Third derivative, -3. So that's easy enough that this number should match that number, the negative exponent. What's going on with these factors of 3 that are coming out? 1 derivative, 1 factor of 3. 2 derivatives, 2 factors of 3. 3 derivatives, 3 factors of 3. So the power on these 3's also matches the number of derivatives. So those two numbers should be the same. So we'll have a 3 to the n plus 1. And then the factorials. So what's going on with the factorials? We didn't quite start seeing the factorial until about the third or even fourth derivative is where we really start to see it. Third derivative, well, it's just a -2. And of course, -2 times 1 is 2 factorial. Fourth derivative, we saw 3 times 2. Fifth derivative, 4 times 3 times 2. So we have a factorial, but it starts 1 less than that guy. So since this is n plus 1, 1 less than that should just give me an n factorial for the factorial coefficient. And now the last piece, we go back and see, well, it's alternating, but we just want to make sure we start at the right index. And this one is easy, is one that's kind of easy to screw up because, right, the 0th derivative, the original function was positive and it went positive, positive. And then it alternates just because of the weird nature of natural log. Once we actually get into these rational functions, it'll start to alternate with successive derivatives. So 1 derivative positive, 2 derivatives negative, 3 derivatives back to positive. Did I mess that up? 1 derivative was positive. When I take 2 derivatives, I should have that negative come out. And so because that guy was negative, when I multiplied by that -2, that should have taken care of that negative and been positive. Then when I multiply by that -3, this guy should have been negative. And then, of course, multiplying that -4 makes that guy positive. So again, minus signs, not a big deal. But when you go back and then check, hey, I noticed my error. of where I was messing up the minus sign. So let's go back. We've got our first derivative positive, second derivative negative, third derivative positive, fourth negative. And so the first derivative corresponds to n equals 1, or excuse me, n equals 0. If n equals 0, I should have a positive here, which means -1 to the 0 gives me that positive. And you can check again at second derivative, we had a negative. So that would be n equals 1 here, gives me the second derivative, n equals 1 there, gives me a negative value. So it's kind of just like reverse engineering these sequences in series, except now you might have a lot more going on because you're having the compute derivatives is one thing, but then you have to kind of recognize what are the sequences that are coming out with these constants. We had a 3 to the something, 3 to the n plus 1, successive powers of 3, and then we had a factorial going on. And then the exponents usually aren't too bad, since those are usually just a linear sequence in the exponent.
Thank you. That really helped.
Other questions?
I got a problem here. It's telling us to use a degree or a third degree Taylor polynomial centered at 0, and our f of x is e to the negative x. It says according to Taylor's inequality, t sub 3 of 1 approximated e to the negative 1 with an error less than, and then you find that error. Could we go over how to do that?
Yes, we were approximating e to the x with t3.
Yeah, e to the negative
E to
x.
the negative x. So nicely enough, since we know e to the x, we can find the polynomial very easily. It's centered at 0 though, yeah? Otherwise,
Yeah,
it would
it
be,
says it's centered at 0, and that we used 1 for x whenever we went to do our
we
error
plug in,
bound.
yeah. So the third degree Taylor polynomial, we just plug in our n from 0 up to 3. So we will have 1 minus, when n is 1, we will get x plus squared over 2 minus x cubed over 3. And then we want at x equals 1. Of course, when we evaluate it, 1 minus 1 plus 1/2 minus a third. And it looks like we get a sixth. So the ones cancel. 3/6 minus 2/6 gives me 1/6. And we want to know how big of an error.
Yeah.
So since here our x was 1, our interval is 0 to 1. So we find m, which is a bound for the fourth derivative on that interval. Nicely enough, of course, what's the fourth derivative? When I take the absolute value, we're going to get the same function back. And we know what e to the minus x looks like. Oop, it's going to be a decaying function. And our interval is between 0 and 1. So our maximum is at the left side of the interval. So maximum is equal to 1, and that's our m. So then our error bound is less than or equal to 1 over n plus 1 is 4 factorial. And then x minus a was just 1 minus 0 to the 4th. So the error is within 1/24th.
Okay, yep, I got that one right. I just wanted to make sure I did the process correctly and didn't just somehow get it right. I don't know.
Yep.
As far as the applications of differential equations, I remember you saying we should expect to see a mixing problem. What about logistics equation or exponentials? Or
Like exponential growth and decay are pretty straightforward. Hopefully, with just, I mean, the pretty easy differential equations. Logistic problem, I don't think it's on there.
okay, yeah, I'm just trying to decide how to like divvy up my study time if I need to study something that may not be on there or will be.
Yeah, I'll go ahead and let you guys know that. Yeah, you don't really need to know the logistic equation. It'll probably be on the final. Yeah. Logistics. It's one of those ones where it's like we're in a midterm where we've got, you know, only a couple questions can really be short answer, and the logistic equation would be something that should probably be a short answer question. So unfortunately, it didn't make it on this one. All right, so I got to get going. I want to get some lunch, but then I will be on at least by 5:15. If I can be on a little earlier, I can try, but I'll probably be busy at least up until 4:30. So I might be able to sign on, I don't know, 10 to 15 minutes early. I'll let you guys know if I can, and I'll send an email out.
All right, thank you.
Yep.
Thanks.